this video, we're going to learn about something called percent yield. Percent yield is how we calculate how well you conducted your lab, okay? And mathematically, what that looks like is before we do a lab, we will calculate how much product we should theoretically produce, okay? So when I talk about theoretical product or theoretical yield, what I'm referring to is what we calculated out, like how much we should actually make from a lab, okay? Actual yield or actual product is how much we really made in the lab. So those numbers usually aren't the same numbers. For example, I may theoretically want to get 4 videos filmed and edited in one night. But actually, when I realize that my favorite show is coming on and I'm super craving froyo, it may end up only filming and editing 1 video. So your theoretical yield is what you plan on making or plan on doing, but actual yield is what really ends up happening. And usually it's less than what you planned on doing, okay? So let's write out these 2 terms because they're going to be important terms in this lesson. The first is theoretical yield. So theoretical yield is whatever we planned to make in the lab or whatever we calculated, okay? And we can find this, you can always find theoretical yield by taking grams of your reactants, okay, and then converting to how much product would be produced. The other term that I mentioned was actual. What do you actually produce, or what is your actual yield? Remember, yield just means like what we produce after the arrow, okay? So actual yield is what really happens. So I'm going to say what we measure in the lab. This is what's actually produced, or what we like measured in the lab, like we measured that we produced this much, okay? So percent yield is really just the percentage of product that you make. How close was it to what you were supposed to make? So you would take your actual yield, so whatever you actually did in the lab, and you would divide it by whatever you were supposed to make in the lab, okay? And then you always multiply that by 100. Anytime you have a decimal, you want to make it a percentage, you always multiply by 100. So it's actual yield divided by theoretical yield times 100. Okay, and I'll write it up here too so you can see it again. Actual divided by theoretical times 100 will equal percent yield. That'll tell you, it's kind of like your grade for how well you did what you were supposed to do. For example, my actual was 95% of what I was supposed to make, so that's really good. But if my theoretical yield was 35%, that means I only made 35% of what I was supposed to make in the lab. So you can kind of think of it in a grade standpoint, okay? So 35 would mean you failed, you didn't produce as much as you were supposed to, and a 95 meant, wow, you did the lab really, really well, you produced what you were supposed to. Okay, so let's talk about how we calculate this out. I wrote several steps here, so I want you to write down these steps. So the first step you do is you write out your chemical equation. And that means you have to even out the charges on compounds. Okay, so for example, if I have an element and then I have another element or a polyatomic ion, you'd have to even out charges to make sure you had an even compound. So even out your charges and then watch out for diatomics. Remember, that's H and then the magic 7, okay? That starts at nitrogen because it's the 7th atom. And it goes nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. And astatine, which we never use, okay? So these diatomics, anytime they're by themselves, they exist as 2s, okay? So make sure you watch out for those. Next thing you do is you balance the equation using your coefficient. So a coefficient is that big number that goes in front of the compound. Okay, so you're really counting atoms here. And then the third step is we actually look at the problem and we find the actual yield. This is always given to you in the problem. So you have to find it and label it. Think of some some words you should look for to identify your actual yield. Is so-and-so made this in the lab, that would be a hint that that was the actual yield. Or if they say so-and-so produced this much, then that's another hint that it's the actual yield. The last step is to just get your theoretical yield. So you'll need to calculate that out because usually you're going to be given grams of your reactant. It'll say we use 10 grams of blah, blah, blah to make, and it will tell you how much they made. Well, the reactant is going to allow you to calculate your theoretical yield, how much you should produce in the lab. So you're going to do a grams to grams problem, going from grams of the reactant they give you to grams of the product that you're trying to go to. That will be your theoretical yield, and you'll put that in your percent yield equation. Now, sometimes you won't have to calculate theoretical yield. Sometimes they will actually just give you the number. And in that case, they probably won't give you a chemical equation, and you probably won't have to balance it out. And our first problem is like that. Our first problem is simple, showing us just how to use the percent yield equation. But our second example is more complicated. We have to find theoretical yield. Okay, so I don't have to balance this equation, and I don't have to write it out, and I'll tell you why. Because it says Marvin K. Mooney was conducting a lab where he produced sodium chloride. Marvin measured is a key word. What does that mean? It means the number we're about to hear about is actual. Okay, it's an actual product he made in the lab. The sodium chloride he produced was to be this much. This is how much he actually produced. This is our actual yield because we see the word measured. But Marvin calculated, here's our other hint word, he should have theoretically made this many grams. So this is our theoretical. See how they gave us the theoretical yield? If they give you the theoretical yield, you don't need to have an equation because you don't have to calculate theoretical yield. So all I do here is I put my actual grams of product divided by my theoretical grams of product times 100. Be sure that this division is in parentheses. You can't type in your calculator 23.4 divided by 27.2 times 100 because it's going to have this 27.2 times 100 instead of your fraction. So be sure that you put the actual and theoretical in parentheses, then times 100. And so that's going to give us 86.03%. That's an okay theoretical yield. Ideally, you have something in the 90% range, but this Marvin did okay in the lab. He produced 86% of how much he thought he was going to produce. Okay, let's look at our second example. In this example, as we read it, let's look at the numbers that it gives us. It says Duncan was decomposing potassium chlorate into potassium chloride and oxygen gas. He used 32.5 grams of potassium chlorate, and he found that he produced 15.2 grams of potassium chloride. Duncan became stressed about his percent yield and began to eat donuts. What was Duncan's percent yield? Okay, so let's look at these two numbers. It's easy when you're doing percent yield problems to think you're given actual and theoretical in this problem, but you're not. It says he used 32.5 grams of potassium chloride. Used, does that mean that this number is a reactant or does it mean it's a product? If he used this many grams, that means this is a reactant. We're given a reactant. Now let's look at the next term. He says he produced in the lab. So what does that mean this number represents? If he made this in the lab, this is his actual. If I'm not given theoretical, which I'm not, I'm given actual yield and I'm given grams of a product. If I'm not given theoretical yield, I have to follow the steps above. Okay, the first step was to write the equation. So that's my first step. I'm going to reread the question and I'm going to find my reactants. I'm going to find my products. I'm going to write them out. Okay, we're decomposing potassium chlorate. Okay, potassium is K. Chlorate, I have to look on this because remember it ends in 8, which means it's a polyatomic. So chlorate is ClO3. I look on the polyatomic chart and chlorate's charge is -1. Potassium's charge is +1. So see how they even each other out? I don't have to put any numbers at the bottom. He's decomposing this guy, potassium chlorate, into two different things, which means potassium chlorate is the only reactant. Another hint that potassium chlorate is the only reactant is that he uses the word decomposing. Remember, a decomposition reaction is when you have one reactant and multiple products. Okay, so what are we decomposing this into? We're decomposing it into potassium chloride and oxygen gas. Potassium is K, chloride is just chlorine, which is Cl, and now I have to even out their charges because it's a compound. Potassium's charge is +1, chlorine's because I look on here. and that means their charges are even, and I can leave them like that. Now I'm also producing oxygen gas. Oxygen is a diatomic, like we just talked about, which means it's going to be O2 when it's by itself. Okay, so now that I've written the equation, I need to balance the atoms using coefficients. Okay, so I see my potassium on both sides and my chlorine on both sides are even, right? I have one potassium here, and I have one potassium on the other side. I have one chlorine on the left and one chlorine on the right. The only thing that's not balanced are my oxygens. So I have a 3 on one side, see that? And I have a 2 on the other. I'm going to go to the, I don't know what that's called. Math is not my strong point. It's like the least common multiple. Is that what it is? I think that's what it is. We want to go to a number that both can go into evenly. And so I'm going to choose 6. I'm going to choose to make 6 oxygens. So if I put a 2 here, I get 6 oxygens. If I put a 3 here, I get 6 oxygens. But I have now changed my potassiums and chlorines. I have 2 potassiums here, 2 chlorines here. So all I have to do is put a 2 here, and now I have a balanced chemical reaction. Step 3 was labeling my actual. So my formula should look like this. Actual divided by theoretical times 100. My actual, I already decided, was 15.2 grams of potassium chloride. That's KCl. And I just need my theoretical grams of potassium chloride, right? That's what I need to calculate. So that is my 4th step. Step 4 is finding how many grams of potassium chloride you theoretically should have produced. Well, remember, we've done this before where if I gave you a reactant, I tell you how much product should I make. Well, that's the problem we're doing right now. How much reactant did I give you? Well, I gave you 32.5 grams of your reactant, which is potassium chlorate. So that is your given over 1, okay? Then when you're calculating your product, we're going from grams of potassium chlorate to potassium chloride, which is my product. Okay, so we're tracing our path. This is just now a regular stoichiometry problem. I'm in grams of A, okay, grams of A, and I'm going to grams of B, which means what do I have to go through first? Moles, right? You always have to go through moles. I put moles of A, which is potassium chlorate, right? Okay, so I'm in moles of A, and then in order to get to my other compound, you always have to go moles of A to moles of B. So I'm going to go moles of B here, and B is potassium chloride. Okay, so this is B. Now that I'm in moles of potassium chloride or my product, I can go to grams of my product. So I go grams to moles to moles to grams. So now I'm going to draw my lines here. I'm going to erase my arrows. So now I take my unit that's on the top, and I'm going to put it diagonally on the bottom so it can cancel out. So I want grams of potassium chlorate to cancel out. And then moles of A is on the top, so I'm going to put moles of A on the bottom, so they cancel. And then lastly, I have moles of KCl on the top, so I'm going to put moles of KCl on the bottom, and they cancel out. So I'm left in grams. Okay, so now I just have to insert my numbers. And so I know that anytime I have grams and moles, I'm doing molar mass, okay? And so the molar mass of potassium chlorate, when I calculate it out, should be 122.551. And then 1 always goes next to the unit moles when you're doing molar mass. Now I have moles over moles, see that? That's always going to be coefficients from the balanced equation. So how many moles of KCl do I have? Well, I have 2, so 2 goes here. How many moles of potassium chlorate do I have? I have 2, so 2 goes down here. And then the last one I'm doing, oh, I forgot my multiplication signs. The last one I'm doing is molar mass again, grams and moles. So remember, 1 always goes next to the mole when you're doing molar mass. And then I have to find the molar mass of potassium chloride, which is 74.551. So now that I've set it up, I multiply the top, multiply the bottom, divide them, and I get this many grams of potassium chloride, 19.8. What does this number represent? This represents my theoretical yield. So I take actual, I divide it by theoretical, I multiply it times 100, and then I get my real answer, which is, by the way, 76.8%. So Duncan kind of should have been stressed about his results and should have been eating donuts because he barely passed. And that is it for your 10.4 video in honor of it being the last video in one of the hardest units, stoichiometry. I have a fun little surprise for you guys that will haunt you for probably the rest of your life. Congratulations. Enjoy.
I am a mole and I live in a hole. I spend my days digging through the clay. When you call me and I can't be found, look for me underground. Live in a hole, yeah, 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 yeah. Sleep in a hole, yeah, 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 yeah. Dig in a hole, yeah, 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 yeah. 'Cause I'm a mole. Live in a hole, yeah, 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 yeah. Sleep in a hole, yeah, 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 yeah. Dig in a hole, yeah, 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 yeah. I am a mole and I live in a hole. I put my head up, you can see my snout. It's long and thin to put the dirt about. And in your garden I'll dig lots of holes. And then I'll dig some more. Live in a hole, yeah, 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 yeah. Sleep in a hole, yeah, 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 yeah. Dig in a hole, yeah, 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 yeah. 'Cause I'm a mole. Live in a hole, yeah, 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 yeah. Sleep in a hole, yeah, 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 yeah. Dig in a hole, yeah, 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 yeah. I am a mole and I live in a hole. Why don't you visit for a